Hello, I'm Joshua, and I am a programmer, the head programmer of Stealth Robotics. So I like to program in my free time, and I've learned a lot of content that isn't taught in schools. So, for example, here today I'll be talking about concurrent programming as well as parallel programming. And I feel like this is a topic that is overlooked, at least in the high school like AP curriculum. And I will be talking about it more today, and it will be very useful if you ever want to do processing with a lot of data, or if you want to work with control systems. So the key points I'll be talking about today would be why this is an important concept, the difference between parallel and concurrent programming, threads, and state machines. So we're going to talk about why this is an important concept first. So let's say you have a system where you want to control two things at the same time. So if you, for example, are a robot, our robot has a claw, an arm, and it has a drivetrain, right? So you would want to be able to drive the robot. But at the same time, if you want to pick up a cone, you would want to close the claw and then wait for the claw to be closed before you lift the arm, right? So if you were to just do it normally, like sequentially, so if you look at that picture at the bottom right there, that is a sequential system where you wait for task one to be finished. And then once task one is finished, you will say, okay, so we will now start task number two. And then after task two is finished, you start third task and so on. So in this case, it would be, we're going to give the command to close the claw. We're going to wait for the claw to be all the way closed. And then we're going to issue the command, lift the arm. And then we're going to wait for the arm to finish. Then you can drive. But that's not a very effective system because then you're just stuck. You can't move. So if you were to miss the cone, for example, you wouldn't be able to reposition yourself until this whole sequence is done. And it also prevents you from being able to, let's say, move before the cone is already finished going up. So that is kind of like the second point, responsiveness. So especially in certain applications, like for example, in web. So when you go to a website, there's a bunch of JavaScript code that runs in the background, and that's all asynchronous. Because if I were to have a task on the website that says, okay, we're gonna do this, and it waits for that to complete, then your web page is never gonna load. It's gonna be really slow because it's gonna wait on all these different tasks to finish, and that's not a very efficient model. So we're gonna first talk about parallel programming. So this is the standard approach to doing multiple things at once. And it effectively creates multiple workers for the same task so that multiple tasks can be run at the exact same time, which is known as parallel. So there's a significant performance benefit to running things in parallel because you effectively double the amount of work you can do at once. So if you look at the picture at the bottom, you can see that both task one and task two are being run at exactly the same time. However, there is a small like performance overhead, or which is like a cost to creating these threads. But if your task is large enough, this is definitely worthwhile to consider as a potential solution to the problem of having to do multiple things at once. So you might be wondering, oh wait, no, I want to give an example first. So consider this. You have a bunch of boxes and you want to move these boxes from point A to point B. So in a single threaded example, which is how programs normally run, you would have one worker which goes to grab a box one at a time and then goes from point A to point B, grabs the box, point B to point A, deposit the box, and then go back to grab another box. Now, there's nothing wrong with this way of doing it. It's just that it's not very fast and you don't have the ability to do anything else, which is why a threaded application is the way to go here, because you can have your main thread do something and then your second thread do something else. So your main thread can be still responding to things while your second thread is working. Or in this scenario, you can have both of them doing work. So in this case, you can have multiple workers that all go and grab the boxes from point B and move them back to point A. So you effectively increase the speed at which you can move these boxes. And that is oftentimes what you want. So in a threaded system, you use multiple cores. And as you can see here on the right is a graph of CPU usage. And you've probably seen this, and this is just a picture pulled from Task Manager. And you can see each of these squares is one of the CPU threads, and you can see how each of them is doing work. And that's how your computer is able to do all these different things all at the same time. And but the problem with this is, as you can see here, they're using the physical cores. If your system doesn't have this number of cores, the CPU will actually play a trick on you where it pretends like it's using multiple, but it just is just switching back and forth between them. And that's not good because you're having the performance cost of starting a thread. It's not like a free operation. It has a cost to it, but you're not gaining the benefit of being able to do multiple things at once. So that's why you want to make sure your system can actually support multi-threading before you start multi-threading. And there are other problems with multi-threading too. So there's a concept called locks. So essentially, sometimes an operation can only be done by one thread at a time. And this is oftentimes just a security mechanism so they don't mess each other up. So if we go to the example on the next slide, we have think back to the previous example with the boxes, right? So you have all these boxes you want to move. So you have your workers go and grab the boxes. Now imagine if one worker goes to grab a box, right? And then a second worker also goes to grab the same box. Now two things can happen. Number one, the box is already gone because the first worker already took it. Now the second box might just freak out and crash now because it doesn't know what to do when there's no box there that it's assigned to grab. And number two, what can happen is they can fight over the same box because worker number one says, oh, this is the box I'm supposed to grab, and worker number two says, this is the box I'm supposed to grab, and then they fight over the same box, and that is oftentimes not the desired result. So what a lock effectively does is it kind of puts like a security personnel basically that says, okay, only one worker is allowed to go inside the warehouse and grab a box at a time. So that kind of prevents the two workers from fighting over each other by essentially saying that you can only do one at a time. Now, of course, you still get the benefits of being able to travel the distance with two workers because there's still a distance between A and B. So you still get that benefit, but loading the boxes, you can only do one at a time. So that's what locks are. But there's also another component of unpredictability. So let's say I have all these boxes. Let's say I have two boxes, so A and B, and I have two workers. I tell worker one, grab box A, worker two, grab box B. There's no way to predict which box will arrive first. Will it be A first or B first? It's all up to how the CPU decides to schedule these tasks. So that unpredictability is oftentimes not very helpful to debugging code because you have to deal with the randomness, which you will have to be taken into consideration. And another note on these locks. So the reason why a lot of times in FTC, especially robotics, you won't want to use locks is because of, you won't want to use threads is because of the locks. So each of the ports on the Rev control hub only allows one thread to interface with it at a time. So for example, let's say you have a motor in port 0 inside of the control hub. You can only have one thread that actively communicates with that motor. If you try to add a second thread that also tries to communicate with the same motor, it won't actually work because the program effectively says only the first thread can actually send messages to the motor and the second one just kind of sits around. And that's oftentimes not what you want when you're trying to do multiple things at once. You don't want all your messages to be blocked and the motor just kind of sits there. And there's no way to really tell which thread is actively working on it. They kind of just fight each other because when one thread is done, it opens it up for the second thread to join in. But as I said before, you don't know that the first thread is done before the second one goes in. So then you have to implement some like really complex system to kind of schedule the tasks. And that's oftentimes not worth it. So go to the next one. Okay. So we're going to now talk about, actually, there's one more example I want to say. So the camera, so if you ever use Easy OpenCV, which is just like a library to make cameras work on your robot, the camera actually runs on a separate thread. And the reason for this is because by running the camera on a separate thread, you can do all the camera processing without taking up the precious processing power of your main thread, because your main thread might have to do a lot of computations, such as, your path finding, your controller stuff. But you don't want but the camera also needs a lot of processing power to do all those, filters or clips or whatever image processing steps you're doing, and that requires it to be run on a separate thread so they don't fight each other for computational power. And the reason that it's okay that this is on a separate thread is because only one thread is actually communicating with the camera, because the EasyOpenCV thread communicates with the camera, but there's no other thread that also wants to communicate with the camera. So that's why in this case, it's okay. And when I talked before about your processor having to need multiple cores in order to have multi-threading, that's also satisfied in this scenario because your Rev Control Hub actually has 4 cores, which means it is capable of multi-threading. Okay, so now we're going to talk about concurrent programming. So this is another way to achieve the goal that we set out to achieve at the beginning, which was to have multiple tasks be done and have that responsiveness. And I mentioned before briefly that this is the model that web pages like to use in order to make things work. So the way the web pages do it is they actually have it so that they're what are called like callbacks. So it waits for an event to happen, and then once the event happens, it triggers your callback, which is just like whatever you want to do. So let's say like you have a button, you can add a callback that says, oh, if this is pressed, I'm gonna do this, change the button to red. I don't know. Any task doesn't really matter. And the reason for that is so that you don't have to make a loop and say, okay, is button pressed, and then change it to red, and then just keep looping and waiting, because that would make your website slow down or just stop completely, which is oftentimes not what you want. So in this case, the tasks take turns running. So if you look at this graph, you can see that task 1 and task 2 are both being processed, but neither of them are running at the same time. They're running completely separately, but they're both being processed in the same period of time. There's no one after the other and waiting for one to complete. So because this is only running on one thread, there is no benefits because performance benefits, because you only always have one worker. So you don't get to do 2 things at once. So an example for this would be if you have like a chef in the kitchen, right? So you have multiple tasks you want to be able to do. So let's say you have like rice, you want to cook your rice, you would put the rice in the rice cooker, right? You would wait for the rice to be cooked and you would take it out. You have a pizza, you put the pizza in the oven, you would wait for it to bake and then you would take it out, right? Or if you have a soup, you would have to, cook the soup and then you turn off the stove, right? So in a single threaded system, it would be, we put the rice in the rice cooker, we turn on the rice cooker, we're going to sit there and stare at the rice cooker until it's done. We're not going to do anything else. We're just going to wait for the rice cooker to finish. Now that's a pretty bad system, because once that's done, you have to move on to your next task, which is, let's say, cooking the pizza, and you're going to have to, once again, stare at the oven until the pizza is done. And your whole meal is going to end up taking a lot of time to be finished. And you'll end up spending most of your time just staring at your kitchen appliances, which is not an efficient way of spending your programming resources at all. So what parallel programming does is it says, okay, so instead of having one cook, we're just going to have 3 cooks. So one cook is going to stare at the rice cooker, a second one will stare at the oven, and the third one will stare at the soup. Now, this is still very inefficient because most of these threads are just kind of waiting. They're not doing anything. But the benefits over the single threaded version is that at least you're doing all of them at the same time. You don't have to necessarily wait for one of them to complete before you do the next one. But you're just kind of wasting a bunch of processing resources just sitting there and waiting. And you might have to worry about certain locks that you don't know about. So what concurrent programming would be is we still go back to the original one where we have one cook, but instead of having the cook kind of just sit there and stare at the appliances, you have the cook go around the kitchen and look at each of the appliances in sequence. So it would first, look at the rice cooker, is it done? Then it would look at the oven and check the pizza and see if that's done. Then it will look at the soup and check that, and it'll kind of just go around in a circle. So that way it's not using any time, just kind of sitting there waiting for one of them. So all 3 of them can be done at the same time for more efficiency without even having to use multiple cores. And this is really important in lower end systems that don't have those multiple cores. Or if you want to use that core for something else, now you can free it up to be used. So now we're going to talk about the state machine. So a state machine is a way in order to achieve the concurrent programming I was talking about before. So the way a state machine works is you effectively have a loop, well, and states inside the loop, which each state just represents like a step. And your state needs to have a condition, and this is the condition that must be met before this step is run. And you need to consistently update it, which is why the loop is there. However, technically, you do not need a loop if you have some other way of refreshing this state machine. So on the right, I have like pseudocode, which will explain the logic of how it works. So you have a state variable, you set it to value, it could be 1, 0, it doesn't matter, it just has to go up. Then you check if the state is equal to 1 in this case. Then if it is, then we're going to do the starting task 1. We're going to do that. And then we're going to add 1 to the state. So now state is 2. So we're going to then go down here and do your other tasks. And the important part here is you have these chained if statements. So you might be wondering, well, I added 1 to the state, why doesn't it immediately run the second state? Well, that's because I have this other condition right here. So what this condition is, it's saying, okay, so before we run the second state, we must meet this condition. And because state is now 2, this part, the first part, state 1, will no longer be run. It is done. So you can chain all these together. You can have state 1, 2, 3, 4, whatever. So that way you can have a sequential task that has blocking to it. As you can see here, it waits for some condition. However, at the bottom, you can still see it does other tasks. So you can have something else be done while you're doing that without having to worry about them blocking each other and preventing you from doing the things that you want to do. So an example for this would be, let's go back to the example of a cook in the kitchen, right? So before we had all these different tasks, let's make another example. So let's say you're cooking a soup, right? You would want to put the meat in the soup first and then let that cook for longer than the vegetables, right? So let's say state 1 is you put the meat into the soup and you turn on the heat and you let it cook. Then you can be, watching TV, for example, while you're cooking, and you wait for that soup to finish cooking for, let's say, 10 minutes before you add your vegetables. And by having this state machine, you can be able to do your other tasks, which, let's say, it's just watching TV while you're waiting for the first task. You'll periodically look over and check the soup, but you won't have to be sitting in front of the soup staring at it. But at the same time, you can have this multi-stage process where you wait for something instead of just being like, oh, I'll just start everything at once and hope and wait for them to all finish at once. And if you were to do this sequentially, you wouldn't be able to do that. You would have to sit there, wait for this to cook 10 minutes, then you would add your vegetables, but you wouldn't have time to do anything else. So in this case, I'll explain how it works for our robot. For example, you would, say, okay, so we're going to loop. So if the state is 1, we're going to close the call. Then we'll add 1 to the state. Then we'll say if it is now state 2 and a certain amount of time has passed, so like the call is done closing, we're then going to say we're going to lift the arm and then we're going to add 1 to the state so that it's done. And the other task would be like driving around. So you would maybe set the motor powers based on your joysticks. So that's how this would work in the setting of robotics. And that effectively concludes my presentation. So I will now take questions.
Great. If anybody has a question, you can chat it into the chat, or I know we had a couple of questions pre-submitted. Tyler, do you want to read those questions?
Sure. The first question is, can you explain PID and odometry?
Okay, so PID is just a system in order to drive error to 0. So PID has 3 components to it. The P stands for proportional. So it literally just multiplies your error by some coefficient and sets that to your power. And the I would be integral. So in this scenario, it's just the sum of errors over time. So if you know what an integral is, you take the error function, you're finding the area under the curve at a certain point in time. It's literally just the sum of the error over time. So Then you have the derivative, which is going to be your change in error. So how fast did your error change? So it's used to get spikes in error. So if your error certain spikes, then it lets your PID respond really quickly to that error. And the integral would be if you have an error that persists for a long period of time, it'll add up until eventually it's high enough that it'll just correct that error. And you set whatever your control system to this. So in an example for like a thermostat, for example, you would have your PID. So let's say you're at 30 degrees, right? But you're supposed to be at 40 degrees. So you take that 40 degrees, you subtract the 30 degrees, you get 10, you multiply that 10 by your P value. Let's say in this example, I'm just doing a P controller, and then you would set, let's say, your boiler's power to that 10. And you would have to tune each of these P, I, and D values until it corrects properly, because 10 power of 10 might be too high and it'll cause it to overshoot. And now you're at 50 degrees, and 50 minus 40, 40 minus 50 is now negative 10, which will cause it to drop and now oscillate in between these two values. So you'll have to make sure that your P value is tuned so that it won't cause it to overshoot or undershoot and cause these oscillations. And your integral value will be like if you're stuck at like 59 degrees and then the correction says, okay, we'll just set the boiler power to like 0.1 or something, and then that's way too low to actually heat up anything. So eventually it'll build up the error, and then it'll increase the boiler power to like 0.2, 0.3, and then eventually it'll be hot enough to increase your temperature back up. And in the derivative, let's say you, I don't know, open a window and let the cold air in from outside. Suddenly your room temperature drops by like 10 degrees. And that's a really sudden drop in air. So the derivative is going to be a high value. And you're just going to set the furnace temperature to that, which will heat up your house pretty quickly. And in robotics is the same thing. For, let's say you're controlling a slide, you have your slide position, you would calculate the error of your slide, so where the slide is supposed to be versus where it is, and you're gonna, instead of setting like a boiler power, you would set the power of your motor to that, so that way you can try to move your slide to the correct position.
Tyler, next question.
How do you perform synchronous movements such as lifting and driving at the same time autonomously?
So it depends. Well, okay, so it's basically the asynchronous thing I was talking about before. But if you're just doing something really simple as lifting a slide, then technically you can just call the command for the motor to lift the slide, because this operation itself is non-blocking because you're just telling the motor to set power. But let's say you want to have multiple stages to that, you would need a state machine because you would have to wait on certain conditions. However, if you just want to say motor go to position, then that's fine. You don't need to have asynchronous programming for that. But if you want it to be asynchronous, you could use the state machines that I mentioned before, or you can use some like weird callback system, but I'll explain that in another lecture.
How do you make your code cleaner and more efficient?
So there's also ways to make your code cleaner, and oftentimes if you want to make your, well, okay, so I guess this is more like condensing code, but like if you want to make your code cleaner, there's several tricks you can do there too. So number one, you should use a lot of the built-in functions in Java. So Java oftentimes has these built-in things like, let's say, the Java util functions interface. That's pretty cool. It has all these different functions that you can incorporate into your programs. And you can also try using more object-oriented programming. So if you have a bunch of code that is like repeated, you can try to put it into a class and have all your different things inherit from it, because why would you want to rewrite the same class over and over again with all this repeat code when you can just have inheritance? The same goes for functions too. So if you find that you have a bunch of code that's just repeated inside of like a body that's not necessarily like a class, then you can just make a function for that, and that will make it easier. I know like Rev Robotics uses Java 8, which doesn't allow for streams, but if you're outside of this, you might want to learn Java Streams, which is a fast way to do like array or like operations on collections very effectively. And if you just want like shorter code, you can try learning some like how to use like ternaries, for example, which is a way to condense an if-else statement into one statement. And you can also use tricks like, for example, like an if statement doesn't actually require you to have curly brackets or new lines. You can just do if, your condition, and then what you want to do afterwards. Or you can also learn how to use things like lambdas, which allows you to condense functions into this really short notation to make it more efficient. And I would say try to eliminate variables where you don't need variables.
That wraps up the questions from the forum.
Great, thank you. Do we have any other questions from anyone on the call? Does anyone want to share any code or ask any questions? We're happy to do some screen sharing. We have a little bit of time left. So if anybody wants to ask a question or share their code and get some feedback from Joshua on code or a particular problem you're having, we're happy to look at that. Tyler, looks like we do have one question in the chat.
What is feedforward and when should it be used?
So feedforward is essentially a way for your robot to keep a consistent velocity. So for example, if you want to use a motion profile, you would want to make sure your robot's movement is following that velocity properly, or else, you know, what's the point of making a motion profile and telling you how fast it's going to be if it's not even going to follow that? So that's essentially what feedforward is. There's multiple different ones. There's one for like gravity, for example. Gravity will always pull whatever components you have downwards, let's say a slide, so you might want to add a little bit of power to it just to make sure it keeps its current position even though gravity is pulling it down. And there might be like a static, so when it's moving there's a certain amount of friction it must overcome, so you might want to add a little bit of power to your slide, for example, for it to overcome that friction and keep its consistent velocity. And that's mainly what feedforward is. And it's used whenever you want to have your system be stable or meet a certain velocity that you need.
Great, thank you, Joshua. Any other questions that anyone has on the call, or again, if anybody wants to present any code or any challenges that they're having currently with their code, we're happy to take a look at it as we kind of wrap up the call today. So I think that's a wrap, Joshua. I want to say thank you to you for your time. Great learning session. Thanks to everyone who joined. Thanks on behalf of Stealth Robotics. If anybody has any follow-up questions for our team, please don't hesitate to reach out. We'll be sharing the presentation on our website and also through our social media. So thanks to everyone, and hopefully we'll be hosting additional sessions in the future on other topics. We'll also send a short survey out so you can give us some feedback on our learning call today and also share other topics that you might be interested in. So thanks to everyone and have a great day.